So we've come to the last talk of today's workshop, and that will actually be given by me. So we will just take a second here to set up the presentation. So to introduce myself, my name is Qirong. I'm an assistant professor here at MBZUAI, as well as the co-founder of Petuum Inc. So, a couple of my colleagues, as well as our founder, Addresing, are all in the audience here. And what I'm going to talk about today is perhaps a little different from all the other talks today, which talked about software and applications, and even to some extent hardware. I'm going to talk a little bit about, let's give it a name, brainware or humanware, which is really about growing the workforce of talent for AI at scale. And by that workforce, I mean the people that actually power the AI at scale economy, the ones that create the models, create the software, deploy the software, connect the business applications together. Okay, as a little bit of a recap of what's happened today, right? We've seen so many examples of models of AI at scale, from code generation to computational biology and drug design to synthetic art, and of course, synthetic writing, the very first application that everyone imagined when GPT-3 hit the news. And to give a sense of the societal impact of AI at scale, right? There was this article on CNN just within the last month, where someone entered an image generated by an AI art generator and won first place at an art contest, and then told everyone about it, and it created this entire controversy. But what I'm trying to signify is that the advancements are already creating a stir in the real world, and if we are, I think, to harness the economic impact of AI at scale, we need to put some numbers to this. And one, of course, of the more famous studies recently, the so-called Foundation Models paper by Stanford University, stated that about 13% of occupations have a primary task that's related to writing. And note that I did not say creative applications in general. This is just writing in language. And the total wage bill of these occupations amounts to hundreds of billions of dollars. Naturally, when we extrapolate applications to creativity in imaging, creativity in coding, or perhaps more scientifically oriented tasks such as diagnostic imaging in medicine, we will find that as long as there are tasks where people are creating something that is similar to something else that already exists, this is the hypothesis for where AI at scale has the impact. And the authors go so far to even point out that the benefits and costs can't even be fully captured by traditional productivity metrics. You won't be able to use GDP to even quantify what impact this will have on society. Now, whether we believe this or not, perhaps depends a little bit on our own internal estimates of the future, but there can be no denying that the estimates of the impact range from significant to world-changing. However, AI at scale also demands a new how-to. As I'm sure you've seen by all the talks that happened today, training one of these models at scale, just to use a very simple back-of-the-envelope calculation, if you take one of these large models and you have to retrain it hundreds of times at least throughout its entire life cycle, because you will need to have new data on it. You will need to change its architecture. You will need to experiment on it. By the time this thing is actually produced, it's probably taken thousands, maybe tens of thousands, maybe hundreds of thousands of GPU years, which is why you should be using a large amount of hardware to train this. But then we also have to talk about the environmental impact, the electricity impact, and all of these issues come together to say that we do need software tools. We also need the know-how, the brainware to use these software, because not everyone is trained to be an expert at running AI at scale or running them on distributed software. But we also need to reduce the cost to be realistic and responsible. And all of that points again to having an understanding of how these systems work. You can't make them better if you do not actually know how they work, is the way I'll simply put it. Now, if we think about, again, the ingredients that go into AI at scale, we have on the one hand the trend towards open source large models that you can now download. You can now fine-tune, as my colleague Hao over here has just stated with ALPA. And that means the software, ALPA, distributed schedulers, as well as the hardware, GPU hardware, high-speed network interconnects. This is all available, but then the question about the brainware, the knowledge to operate these large models, where is it going to come from? And while we could always, positively assume that people will just read online, read blogs, read GitHub, is that actually a systematic way to produce the talent needs for an entire economy, for an entire nation? Maybe it'll work if for the set of people in this world that consider themselves hackers and can adapt quickly to every task. But I personally think that there might be a more systematic way that's needed to train and produce the talent at scale. The talent that's needed for doing the how-to for AI at scale. To give you a sense of why this is an urgent problem, I want to talk a little bit about what I perceive to be a talent shortage when it comes to the knowledge of the how-to for AI at scale. And if we look at the conferences that most of us respect in this industry, for example, NeurIPS, ICML, CVPR, ACL, and of course many others that I didn't name, if you think about the slice of the pie, that papers that are related to using AI at scale, think systems like ALPA, for instance, or think any kind of paper that is really touching upon and improving the state of the art and teaching people how to use the state of the art for training and manipulating these models at scale. Well, what's the size of this slice? I estimated about 2%. So basically 98% of research is not about AI at scale, and maybe about 2% is. Which then points back to the expertise of the people that are writing this paper, and you can now start to see how little talent there is at the moment when it comes to using AI at the scales that we want to. And here's another way to look at the problem. I took this course list here from a master's program at a top AI school. In this list of courses, if you scan all the words that are in here, the word parallel doesn't appear at all. And by the way, this was the set of core courses. If you look at the elective list, the word parallel doesn't appear either. You might also be surprised to know where this university is. I'm not going to say where it is, but that's where it is on the map in the United States. Okay, so I hope I've impressed upon you that although we've talked a lot about the promise of this new generation of prompt models and very large models, the actual amount of talent that's being produced and being prepared to go out in the real world to use these things right off the bat in their first job, or even in their first, say, research career, step into a research career as a PhD student or postdoc. The preparation is simply not there, and you're not going to get it from the academic literature, nor are you going to get it from courses. So now, what about this perspective of the students? Like, I've heard students who have prior experience with an AI job, an industry job. They tell me that I appreciate and I want to learn about parallelism. I want to learn about open source software that makes it work. I want to have the skills to operate these large models. And that's simply because my previous employers or my current employers actually want to see those skills. However, if you're coming in, let's say, from an undergraduate program, or you are making your way through the educational ladder before your first job, these students have a somewhat different perspective. They may not, first of all, even know that these things are happening, or they may not be aware that models like Stable Diffusion or OPT or GPT-3 require these skills. And then there's also a host of other challenges they may face in their preparation. They may not have a computer science or engineering background, so even something like GitHub can be quite intimidating to them. They may find unfamiliar software intimidating because, they don't have a programming background. They may also be unaware of the skills that their employers require. So right now then, even in the talent pool that's available today, preparedness for AI at scale is actually strongly influenced by whether or not they have previous AI job experience. Even the knowledge of what is it that I need to learn is also something that doesn't exist in all students today. So that points to a couple of challenges that educators face when teaching how to use AI at scale. So there is a teacher shortage, which is directly related to the fact that there's a talent shortage, even amongst the research community in artificial intelligence. There is perhaps a state of somewhat low student preparedness. There is a lack of software to do the teaching. There's also a lack of hardware to do the teaching because getting the hardware is expensive. So to build an ecosystem for AI at scale, we will need to grow the workforce of talents in order so that this is not the regime of a small number of companies or organizations, but it's something that can at least percolate down to mid-sized organizations or even small ones like startups. And then the question that I have is, how do we really address these challenges as teachers, right? Is there any part that we can play in this entire process? Okay, at least I will say a little bit about my own modest efforts in this space and how I approach this in my role as an educator here at MBZUAI. And the way I start first has to do with curricula. What is it that we're teaching students? So parallelism, or specifically parallelism for AI, is fundamental knowledge for operating these very large applications. And it turns out that the courses that we get from traditional computer science, even though they exist, they are sufficient and yet not sufficient at the same time. I call that being half sufficient. Part of the reason is that parallelism in AI involves many recently discovered new forms or modalities of parallelism. They have perhaps, the way I would use it, the analogy I would use here is that they have a different set of basic natural laws that in some cases are similar to traditional computer science, and other cases are quite different. And as I pointed out a little earlier, even right here in this year, 2022, almost all of the top computer science and AI universities still lack a specialized course on AI parallelism. So it's left to students to look up advanced literature, look up GitHub, look up blogs, stay on the bleeding edge, literally keeping themselves up to date by scouring the entire sub of human knowledge just to find the knowledge of how to operate these things. So can we be a bit more systematic about this? At least my own teaching experience here at MBZ is that I've developed a course called Parallel and Distributed ML Systems. And the philosophy I've chosen here is to focus on algorithms that are relevant for AI in general, and especially AI at scale. And we call these iterative convergent algorithms, so-called because they repeat again and again and again a set of instructions until they hit a stopping point. That covers essentially 95% or more of artificial intelligence algorithms and applications. And the focus is on these algorithms, as well as their forms of parallelism, the forms of distributed computing, as well as the systems architecture required to make these algorithms work. And then we focus on a couple of key skills that students need to pick up to use AI in the real world at the scales we talked about. One is the design of algorithms at AI at scale, the mathematics of iterative convergent parallelism, to be a bit more technical. How to build the software at AI at scale. What are the systems architectures we need to put together so that an iterative convergent algorithm can be executed over parallel and distributed hardware? And then to actually, finally, and perhaps just as importantly, to check that the AI at scale is actually working. You can't really use what you don't fully understand or can't fully debug. And those are the metrics and theory to evaluate the parallel and distributed AI systems. Okay, so the relevance of, I think, a curriculum is that it would partially address the teacher shortage. Someone has to go out there and develop curricula, textbooks, in order for there to be a systematic form of education for students. But at the same time, it's also addressing the challenge of low student preparedness, the fact that students may not know what is the concepts they actually need to learn to be able to take advantage of all the open source software out there and put together applications for their future employers or perhaps their future businesses and startups that we want to run. Now, is that actually enough? I don't think so, because there is also the matter of giving students practical experience with using the tools that are required for conducting AI, whether it's these large models or whether it's even modest-sized models, but scaled out to very large business applications and data sets. So it's my belief that there's also a need for an interactive lab environment where, given, say, access to computing, whether it's students' personal computers or university computer labs, Is there a way to connect them up to a set of servers that has something called an AI operating system, where the purpose of the AI operating system is to really support classroom teaching with a practicum environment, a software come hardware environment where students can actually pick up the operational research, or simply, let's call it open source engineering skills for doing AI at scale. What would this actually address? Like, what would we want for this interactive lab environment to achieve? Well, some of the challenges in designing such an environment are that, first of all, there isn't very many teachers today, so we have to pull ourselves up by our bootstraps. How do we make it such that such an environment can be taught by someone who was maybe a novice at AI at scale and just a few months ago, but after having gone through some learning, or even some of the some use of the system, then becomes qualified to teach others, right? So how do we actually generate that pool of folks who become masters, become experts in a short period of time? We also have to ask, well, what is the set of software skills that we actually need to be teaching for students to learn AI at scale? And finally, there is the fact that this shouldn't be too diverged from real-world engineering needs. And that's how do we really take this environment and deploy it in different settings, whether that's a university data center environment, a university HPC environment, or university cloud environment, for instance. How do we make sure that this lab environment works in any place? So the way I've approached this, together with my colleagues at Petuum, is that we've been creating a set of tutorial-style, self-contained lab sessions that last an entire semester, one semester's worth of teaching at MBZ. So they can be inserted into a course that has a parallel or distributed teaching requirement. And because they're tutorial style and self-contained, they've been tailored such that a master student can actually complete them themselves and even actually begin to teach other students using this material. Right. The curriculum is really about building, operating, experimenting upon parallel AI applications, involving quite a lot of open source software, including the software that we've talked about in the CASL ecosystem, for which this workshop gets its name, but also more common DevOps and MLOps software, such as Docker and Kubernetes. And again, the practical skills, we talk about what is it that students want to take away, right? It's about understanding how to integrate and interface different pieces of open source. It's about understanding the different parts of an MLOps lifecycle. It's also about the basic skills needed to use clusters effectively, especially in a setting that is containerized and has technologies such as container schedulers, right? It's about experimentation, it's about tuning, it's about parallelism, it's about pipelines. Now, these are very many concepts to teach in a very short amount of time, but it's important that students get the exposure to them so that they're ready for using and deploying, again, these models at large scale. Just as a little reminder, because this is also the closing talk for the CASL ecosystem, the CASL project is a consortium of different pieces of open source software that address three needs: the composability of AI applications, the automatic tuning and tune-up of these applications, as well as the scalability of them to whether it's scaling up in the amount of data, or scaling up on the model size, or scaling out to a very large number of deployments, right? These pieces of software basically come together in the lab to give students a chance to pick up these skills before they're required to learn them in a more ad hoc, a more exploratory hacker-style format in the real world. Let's also talk a little bit about this interesting point I made about making sure the virtual lab environment can go to any piece of hardware, can go to any environment or system. To do that, I want to talk a little bit about the history of cluster schedulers, such as the venerable SLURM project, which is a 20-year-old job scheduler used in high-performance computing and supercomputing. It was created definitely before the current era of AI at scale. You could even argue it was created before machine learning became a hot topic. And then there is this modern piece of software that we call Kubernetes, which is a way of scheduling containerized applications. Containerized applications are essentially packaged pieces of code that are portable, can go between different machines, and they don't stop working just because you move them to another machine. I think that's the most important attribute. And it's been recently adopted by many technology frontrunners, such as one recent famous example is CERN, the European Particle Accelerator Lab. But it's also being adopted by many AI businesses and research organizations. And what it really does is that it handles the deployment, the management of these containerized and thus well-packaged, well-isolated applications. And that technology makes it work on any cluster and is supported by all cloud vendors. In contrast, for a SLURM cluster, which is the more traditional way we do things at universities, if I take a piece of software and it works on my cluster in the university, and then I take it to the next cluster and it's also running SLURM, there's no guarantee that this piece of software will work. So there's this portability issue that's required before a lab environment is truly, one, able to teach students in a way that I will still be able to use what I learned at my job or at my next workplace. And at the same time, we also want there to be an ecosystem, a way to develop code, tutorials, teaching materials that doesn't lose its relevance as soon as I change the hardware. Right. And speaking of this, I think there needs to be an evolution from, say, the more classic way of cluster scheduling to something that is Kubernetes-based. And that's actually something that's achieved by the software that Petuum produces called Rampart. That allows us to go to any Linux GPU cluster or cloud, which eases development of the lab environment, allows me to take it and make it portable to any other place. But the other thing that's, I think, a little bit more interesting and innovative here is that the interactive graphical interfaces, as well as strong integration with what is considered industry standard tools like Jupyter notebooks, I think that really does accelerate student learning versus the traditional terminal-only interfaces like SLURM. And not really as hard evidence, but there's a little bit of a hint towards that, right? These are some videos taken of students, actually time-lapse videos, who are actually following the tutorial and using the various interfaces from Rampart to Jupyter to the CASL open source projects to design and learn how to do AI at scale applications. And I think that personally this is relevant to, again, the preparedness question that students have when they need to face AI in the real world for the first time, as well as also directly addressing the lack of software, the lab environment that is needed to teach these skills. And I would say not to underestimate how difficult it is for the educator to actually produce such a lab environment, because I certainly didn't produce it myself. I had the help of my startup to do this. But I think it's something that once done for the first time can be taken to other educational settings, whether that's other universities or other workshops, tutorial forums, perhaps, even at some point, maybe a advanced course for recent high school graduates. I think those are the possibilities I'm thinking of as we think about where this interactive lab environment goes to. Now, the only question that I haven't answered here is really the lack of hardware, because everything I've talked about is curriculum and software. At the end of the day, hardware for AI at scale is very expensive. And rather than providing a solution for this problem, I'm going to actually turn it around and say these are the opportunities for other partners in the ecosystem, which is, are you an AI cloud vendor, for instance? Are you, say, an organization that is very rich in computation and has an interest in contributing to the education of students? Well, why not be the first organization to launch a Coursera-like cloud environment for teaching AI at scale? I certainly don't have the resources, but it's conceivable that there are organizations that do and are looking for unique applications on their cloud. And there are some things that other cloud companies have done in this regard. Some, using perhaps my experience in the US as an example, some offer discounted compute hours for teaching. We've heard about research grants and educational grants by the big cloud players in America, for instance. But one very interesting story that we've discovered recently is that many of the large models that were trained, such as Stable Diffusion or Hugging Face Bloom, all of the compute for this training was actually due to a deal struck between AWS and these organizations to provide very discounted compute for these startups to do AI at scale. So not saying that cloud providers should always discount what they're doing, but this is a fact that there are cloud providers that have seen so much potential in this market that they're willing to discount it in order to get an edge over the others. Okay. Now, universities could also help in a given way, right? We have many GPUs often sitting around siloed because they're siloed by research grants. Different professors, different faculty have their own clusters. You know, there's sometimes been talk among us academics about actually could we just pull all of these together into a cloud-like application? Which is an easy thing to say until you need to consider what software you need to pull this off. But I think the AI OS concept that we've demonstrated and the successes we've had in teaching this in the lab environment does suggest it is possible to take all these GPUs, nodes, and pull them together into a single AI OS pool for the purpose of teaching or perhaps for the purpose of research as well. And that's required to reach ultimately the critical mass needed to train or fine-tune these models at scale. We already heard earlier in this talk that you know, somewhere between 64 to 120 GPUs are required for a 10 billion parameter model, and that several thousand GPUs are needed for a model that's over 100 billion parameters. So again, the issue of reaching that critical mass is perhaps, I'm not going to call it an existential one, but it's a very important one for universities to maintain relevance as the SOTA, state of the art in large models, gets bigger and bigger every year. What is it that universities need to do to keep up? Okay, so with that, I'm going to give my closing thoughts and perhaps some open unanswered questions regarding the ecosystem at AI and Skill. So, you know, where will students obtain this hands-on experience with building AI at scale, given that most organizations are not even able to operate at those scales we've talked about today just yet, right? The fact that AI at scale is mostly owned and operated by big technology, but also recently a couple of startups that again have acquired through AWS and other partners the resources to train these models. And do universities have the ambition to fill this ecosystem or talent gap, or perhaps maybe ambition's the wrong word, maybe it's the prerogative, maybe it's a national prerogative that the university needs to fill that. And that requires us to actually be active builders and owners of AI at scale. We have to be producing the large language models, graphic synthesis models, drug design models ourselves. But that means we also need the environment, the software, the hardware, the teaching to be able to pull that off. Ultimately, do universities want to be the definitive place to learn how to AI at scale, or are we going to leave that to the industry, right? And I think that's the open question that I'd like to pose to my fellow academics here. So with that, that is actually the close of my talk, and I will take any questions you have. Oops, okay. Right. All right. You have one online? Yes, go ahead and read the question out.
One online question. Are there any good online programs or courses on parallel and distributed AI for someone who cannot enroll in a full MSc degree at a university?
This is a question for which I would have hoped there was a good positive answer to, but at least in my own searching, I'll put it this way: if even the top universities don't have a course, it would seem unlikely that such courses exist online, and in fact that is the case, where if you try to search for these, the best you will get are perhaps tutorials on how to use a specific piece of open source software, usually to train a specific model or a specific class of models, right? So this is exactly the educational gap that I'm pointing out to, that not only is there a lack of a way to learn this as a non-student of a university, even within a university it's hard to learn it. Even as an industry practitioner, it is still hard to learn this, right? And that is actually the problem I'm calling attention to. The hope here is that by developing these materials and developing the lab environments, we may make this a little bit more accessible one step at a time, but it's very early days. Great. Okay, so So if there are no further questions, then we are now at the end of the day 2 of the CASL workshop. And I would like to take this opportunity to deliver the closing remarks for the workshop. So I think it's a summary of what we've achieved over the last 2 days as a workshop, right? We brought together multiple stakeholders in scalable learning from our industry friends and partners, as well as academia, as well as the CASL organizing committee. And I think the CASL workshop is really the first of its kind workshop where we assemble this close-knit group of highly specialized computer scientists that are skilled in scalable machine learning. And during the research day, which was yesterday, we described state-of-the-art advances in the development of generic software standards that can be used as a springboard for scaling up machine learning, essentially performing AI at scale. Now, the industry day today, and I think this was a more practically oriented session during which our experts would give the kind of advice that details what approaches we need to take to implement scalable machine learning, importantly, approaches that we can use today and now. And then, how do we use this to grow startups? How do we use this to grow and power businesses with AI at scale? And now we expect that ultimately, with the close of this first first CASL workshop, that companies ranging from startups to larger organizations will have a go-to resource in this CASL group to make the kinds of efficiencies, improvements in efficiencies, and to accelerate their business using some of the technology pieces that we've described. But it's also about really the connections that we're making with each other, with the experts. For example, Hao Zhang over here has kindly offered call me for technical support for LPA. So in that regard, right, I think I want to just close on a very upbeat note, saying that this is only the first workshop of its kind that we're holding, and we hope to have future CASL workshops with the same kind of mix between industry and academic participation as we go forward. Okay. Now, would any of my fellow organizers wish to deliver a few words as well, just in case?
Maybe I can offer a few more words.
Great.
Yeah, as Qirong just mentioned, this is the beginning, of a long journey. We want to actually do this type of activities, maybe more frequently. We're thinking about quarterly, if not once, every half a year, to really make sure that our projects, the CASL projects, and also the company of Petuum stay in touch with our industrial partners and friends in here to really build a strong mutual understanding of the needs and also of the solution. So I love to encourage all of you to stay in touch with us and reach out to all my colleagues and collaborators with your needs and with your requests. As software engineer, right? So one of the major kind of source of guidance is actually the clients, the customers. Right? So that's why I really love to stay in touch with all of you. That's the business part. On the personal setting, I have to say that I was so excited and so proud, to see many of my former students and colleagues and collaborators are now literally delivering amazing speech and the talks. It makes me feel almost embarrassed about my talk in the morning. Honestly, it's so obsolete, and you should really follow up with their work and also their talks in the future closely. I can guarantee you that they are the best collection of researchers in the SysML field, and they lead the trend. They are very humble. They said they are catching the trend. I don't believe so. I think that they are actually leading and creating the trend. So I hope that we can together, make this field and also make our business, a even more prosperous one. Thank you very much. Again, any of you want to add a few more words?
All right. Well, I hope I've then spoken well on behalf of all the other organizers. And by the way, Eric and I are not the only organizers. This is the point where I want to give thanks to everybody on the CASL committee who helps support and organize this workshop. So I will just read up some names. Willie Nicewanger, from Stanford. Right. Let's see, is Hector Liu from Petuum still in the room? Okay. He's at the back. Okay, Auric Chow from Petuum. Right. Hao Tang from UC Berkeley. And last but not least, Ziting Hu from University of California, San Diego, who regrettably couldn't join us this week, but he's also been instrumental in supporting and creating this workshop. And that is the list of our organizing committee. Okay.
Maybe let me also add that I want to thank and also the MBZUAI staff team, especially amazing and very, very diligent support. I heard a lot of great words about you, about all of you, about the very, very dedicated and commitment that you deliver. I don't think the program is possible without all your support. You've been taking care of all their hotels and travel tickets, logistics, everything. I thank you for great effort.
Yes, and same for me as well. I'm sure you all are tired. The organizers at MBZUAI, you must be tired of seeing messages from me every day, but I really thank you for your diligence in keeping this program as successful as it was today. Now, with that, so that's the end of the closing remarks, and I will just have a few words to say before we take our break and then go for the breakout sessions.